So hello, today we are going to discuss about hybridization. So this phenomena of intermixing of pure atomic orbitals of slightly different energies and different shape to form a new set of orbitals of equivalent energies and identical shape. So this was the definition of hybridization. So I have already prepared why hybridization came. So the reason was, by valence bond theory it was unable to describe the valency of carbon why it is 4 and like many other atoms. So in carbon we have two half filled orbitals, that is px and py. It is having half filled orbitals, and according to valence bond theory these two half filled orbital represents two valency 2, but it is 4. So in beryllium also there is no half filled orbitals, all orbitals are fulfilled, but it is showing a valency of 2. So how does it happen? So here hybridization came. So let's take a look at the organic compounds where the hybridizations are respectively sp3, sp2 and sp. So first of all we have to look at the energy levels of carbon atom where the electrons are situated. Let's take methane as our example. It is having a sp3 hybridization, as you already know, but we have to find out how it happened. So we have 2 electrons at 1s, 2 at 2s and 1 at 2p orbital in the px py position, and 1 pz is still empty. In excited state what happens is that one electron from the 2s orbital jumps onto the p orbital at the vacant pz orbital of p subshell. Remember, don't confuse subshells with orbitals. P is a subshell and pz, py, px are orbitals, individuals. So what happens that these 3 orbitals and the s orbital forms an intermediate orbital of an equivalent energy, that is sp3 hybridization or sp3 orbital, hybrid orbital, where there are 1s, 1 px orbital, 1 py orbital and 1 pz orbital. So these 3 orbitals along with s orbital forms the sp3. From the name it is sp3, that is 3p 1 s orbital. So this mixing up of different orbitals of different energies and shape forms the hybridization, that is the sp3 hybridization. So let's take a look how this hybridization is formed. So this sp3 hybridization. So first of all learn about the hybridized orbital shape. After the hybridization we know that the orbital s is spherical and p has a bilobed dumbbell like structure, but after hybridization what happens, one lobe becomes bigger and another becomes small. In the structure we will not draw the small lobe because it will make the drawing clumsy, so we are drawing only the larger lobes. So the larger hybridized lobes of the sp3 hybridization, I am denoting the hybridization by this blue pen, that is sp3 hybridized orbital. So we have 4 sp3 hybridized orbital. So these are at an equivalent energy state. So hybridization is nothing but, if we take an example, we have a red color paint and a white color paint. If we mix the red and white color paint we are having a pink color paint, which is also more in amount. This is the concept of hybridization by example. So this sp3 hybridized orbitals forms overlap. This is an head-on overlap, that is the axial overlap with the 1s1 unpaired electron of the s orbital of hydrogen, and this arrangement of the methane is due to the lone pair bond pair and bond pair repulsive strength, that is the lone pair has the highest and by the followed as given. So we have the structure of methane where the hydrogen bonded with the sp3 hybridized orbital, and this is a sigma bond. So this leads to the formation of a sigma bond. So the hydrogen So this hydrogen has one s1 orbital which overlaps with the sp3 and forms the sp hybridization. So now next let's take a look at the ethane. So let's take a look at ethane. So in ethane we have two carbons. Oops, I have drawn it too far, so it will be a bit close, easy for drawing. So we have two carbons here, and each one having all these lobes of sp3 hybridized orbital like the methane. But what will happen is that one of the sp3 hybridized orbital will overlap with the another sp3 hybridized orbital by a head-on or axial overlapping. I have drawn it a bit wrong because both the orbitals will have a similar size. It is a bit wrong, so let's ignore it. So we have our all the orbitals, that is sp3 hybridized. So remember, sp3 hybridization involves the formation of hybrid orbitals, which includes 1s, 1px, 1py and 1pz orbital. And again I am telling that p is a subshell and s is also a subshell. Under p, px, py, pz, these are orbitals. And here we have our hydrogen, and these hydrogens are overlapping. The 1s1 unpaired orbital, unpaired electron is overlapping with the sp3 hybridized orbital to form the sigma bonds and forming the compound ethane with sp3 hybridization. So now let's take a look upon. So wait, I forgot to tell that in sp3 hybridization we have 25% of s character and 75% p character, because the total number of orbital is 4, and if we divide 100 by 4 it will give 25%, and that is how it is calculated. So next, moving on to, so now take a look at SP2 hybridization, and this is usually found in ethene, that is C2H4. So we have to again draw the energy levels of carbon. The ground state will be same, but the difference and the gameplay will be in the excited state. So how the valency of carbon became 4? Because in excited state, the one electron from 2s orbital jumps onto the p orbital and makes 4 half filled orbitals, and thus giving a 4 valency, 1s and 3p. That is how it is giving 4 valency of 4. So now we have two electrons in both 1s 2s and 1 half in p orbital, as you have seen in the ground state of carbon. And in excited state we have one electron jumped from 2s orbital to 1p. So we have 3 p orbitals, that is px, py, pz. And if we draw the hybridized state, what happens is that since it is a sp2 hybridization, which means there is 2 p orbital and 1 s orbital involved in forming the hybrid orbital having an equivalent energy. So these three are, as I already told you, px, py and pz. And remember, again a thing I am telling, that the p orbital is dumbbell shaped and s orbital is spherical shaped. So the hybridized orbital shape of sp3 was one larger lobe, one smaller lobe, and in sp2 the smaller lobe is a little bigger than in sp3 hybridization. So the smaller lobe is little bit bigger in sp2 hybridization than in sp3 hybridization, because here the hybridization takes place between sp1s and 2p. Here the p character is much lesser. So we have 1s, let's assume 1 px and 1 py and 1 pz. So this 3 orbital s px and py. So px, py and s forms sp2 hybridization. So one at x-axis and another at y-axis. So total 3 orbitals, and one orbital left not hybridized, that is forms the pi bond. So we have the s and p. I have drawn it so that you can understand the orbital shape, as I have told you, spherical and dumbbell. So when we draw the ethane, so first of all we have to draw our sigma bonds. So the sigma bond forms between the sp2 hybridized orbitals. So now we draw the another two sp2 hybridized orbitals, which will be later forming the axial bonding with the hydrogen. So these are the sp2 hybridized orbitals. I have drawn it with the blue color. So the smaller lobe I will not denote it, because the smaller lobe, if I draw it, the diagram will become messy, a clumsy one. So this is the sigma bond in between the carbons. So take a look at the hybridized state of energy level. That means we are still having one pz orbital left to be overlapped. So the hybridized state does not, so the hybridization does not include this orbital. So what happens is that this orbital overlaps in a lateral way. So let me explain you how it overlaps. So these two orbital overlaps in a lateral way, the two lobes overlap, and this overlapping region contains the electrons shared between the different orbitals of different atom. So after the overlapping, the atomic orbital turns into molecular orbital, thus a bond. The overlapping of two lobes leads to the formation of one pi bond. So this overlapping is also is called lateral overlapping or sideways overlapping, and the head-on overlapping that I have told earlier, head-on, is called the sigma bond. It can be between SS, PS or PP orbital, but it is a head-on. It is a head-on collision or head-on overlap, you can say, and this is called axial overlap, and this is called pi bond between the lateral overlapping of p orbitals. So these orbitals cannot be shown overlapping in this page because it is a three-dimensional structure. If we fold the page and join like this, it will overlap with the p orbital. So to represent the overlapping of the two lobes, we draw it with a straight line. A straight line. So one straight line represents one overlapping of lobe and another overlapping of the lobe. So remember, two straight line represents one pi bond. A straight line doesn't represent a bond here. The straight line represents the overlapping of the lobes. So we have our 4 hydrogen atom, which is containing 1s1 orbital that is overlapping with the sp2 hybridized orbitals. So this is how the hybridization takes place in ethene, and it is a sp2 hybridization. So now sp, before that again it is containing 33.3% and 66.6%, because it is containing 3 orbitals where 100 is divided by 3 gives 33.3. So 2p orbitals, 2 into 33.3, that is 66.6% p character and 33.3% s character. And in sp we have 50-50, half character of both the orbitals. So now take a look at the formation of ethine. So now draw the, again we have already drawn the ground state of carbon here, so no need to draw it again, but the main gameplay happens in the excited state. So let's draw the excited state. So this is 1s, 2s and 3s, 2p. So now let's draw the electrons. So since it is a sp hybridization, sp 1s 1p orbital involving in the formation of a sigma bond, so the hybridization, so the hybridized orbital, which is the intermediate state, intermediate orbital is formed between the overlapping of 1s and 1p. So the 1s or 1p, let it be px, but we are still left with 2p orbitals which will take place in the formation of 2 pi bonds. Let it be py and pz. So these 2 orbitals left to be hybridized. So we have the 1s and 1p, that is sp hybridized orbital. So 1s and 1p, so we have 2 orbitals which overlap, which hybridize to form sp hybridization, which forms sp2 hybridization, 2 orbitals. And in this case, in sp2 we have 3 orbitals which combine to form sp2 hybridization. And in sp3 hybridization we have 4 orbitals. In ethane it is sp2 and ethane it is sp. So in sp hybridization we have still 2 orbitals remaining, and these 2 orbitals will take place in the pi bond formation, but we have the sp hybridized orbital. So this will form the sigma bond between the 2 carbons. So between the 2 carbons, the 2 sigma bonds are formed by the sp hybridized orbitals. So this 1s and px orbital comes at an intermediate energy level and hybridized to form sp hybridization, and these are the sp hybridized orbitals. And we have 2 orbitals, that is py and pz, remaining to form bond. And as I told you, p orbitals forms lateral overlapping, that is the sidewise overlap. And again, to show this overlapping, we cannot show it in a simple 2D page. So we cannot show it in a page, and this is our pz orbital. I have drawn it with the red color, and the pink is py. So this overlapping cannot be shown in a page because it is a 3D structure. These both orbitals are in different axes, as I am denoting with the pen. So this is y axis, this is z axis. So we should not draw it parallelly, we should draw it axially in an axis, which is a correct drawing. So we join this. Joining must be done correctly because the py should be joined with the py and the pz will join with the pz orbital. Otherwise the structure is wrong, and if we fold the paper it will form the overlap, that is this sidewise overlap of p orbital. So here we have 2 pi bond and 1 sigma bond between the carbon, and the rest 2 sigma bond, that is sp hybridized, forms overlap with the hydrogen atom and forms sigma bond, and there is pi bond with the p orbitals. So it has 1 sigma and 2 pi bonds. So this C2H4 compound has 1 sigma and 1 pi, that is the double bond. And in C2H2 we have 1 sigma 2 pi, that is the triple bond. And in the methane and ethane we have 1 single bond, that is the sigma bond between the sp3 hybridized orbital. So here we have the carbon atom at ground state, and it is again excited to a different state where it formed hybridization. So this whole gameplay is done, the whole case of hybridization is due to the excited state where the 4 orbitals combine to form sp3 hybridization, spy, px, pz, and this arrangement is done on the basis of the lone pair, bond pair, and bond pair repulsion. Any system has a tendency to acquire the less potential energy. So every system wants to have a stable state and thus minimizes the repulsion, and this is the way the molecules are arranged in different plane. So we have pi bonds, one pi bond in C2H4, and it is having a SP2 hybridization by forming one S, one P, one PX and one PY, and in ethine it is C2H2 having two pi bonds by sp hybridization. So it is now concluded and that hybridization is necessary to form these compounds. But we have also some salient features. So what we have learned in hybridization is that mixing of orbital happens to attain an intermediate orbital set, and it also proves the formation of carbon compounds like ethane and methane, and how carbon attains a valency of 4, which was contradicted by the valence bond theory. Thank you. Hope you like this video, so don't forget to give a like and do share this with your friends, and don't forget to subscribe my channel for more pharmaceutical videos coming up.